Good afternoon, all. Welcome to today's BTSYM Lunch and Learn on Tideway's Victorian Embankment Foreshore. So today we are joined by Alan and Florin, who will be presenting about the work they did on the project. To begin with, Florin studied civil engineering at Bucharest Technical University and completed his master's degree in construction project management at the same university. He started his career working on deep drainage systems in Romania. As his engineering aspirations became bigger, he looked for a new challenge and decided to move to UK in 2016 and work on projects that will shape London. Since then, Florin's been working as a site agent for Barhale on projects such as National Grid's Chelsea to Battersea Tunnel and Thames Tideway's Victoria Embankment Foreshore. He now works as Barhale's project manager on a Victoria Embankment Foreshore. Ala, on the other hand, studied structural engineering in Ireland and completed her master's in transportation systems strategy and management at the City University of London. She has undertaken roles in tunneling and heavy civil projects from the perspective of the subcontractor, the main works contractor, and recently as a part of program manager team representing the client at Tideway. Ala has added experience of construction delivery on complex projects and within strict regulatory environment, including London Underground's Bond Street station upgrade, Crossrail's Fisher Street, High Speed 2 enabling works, and most recently, of course, Tideway as a construction engineer and NEC supervisor for multiple sites that included Blackfriars Bridge, Foreshore, Albert Embankment, and Victoria Embankment. Alan now works as the sub-agent for Strabag as a part of main works contracting team on High Speed 2's Area South. She also serves on the BTS YM's Schools and Universities subcommittee. So on that note, over to you, Alan.
Shortly by shaft sinking, including the methodology that we used. We'll briefly mention the base lab, and then we'll finish up with what I think is one of the most challenging and interesting engineering feats at Victoria, the short connection tunnel. So just the project overview. So why Tideway? Well, in the 1860s, Victorian engineer Sir Joseph Bazalgette created the sewer that we still rely on today, comprising of more than 300 million bricks. He built it for a population twice the size of the 1860s, 4 million. But the current population is approaching 9 million. Now, while the sewers do remain in excellent condition, they lack the capacity to meet the demands of our current capital. As a result, 39 million tonnes of raw, untreated sewage overflow the system and spill into the Thames every single week. And that's where we come in. At Tideway, we're upgrading the London sewer system to cope with its growing population. Our 25-kilometre tunnel will intercept, store and ultimately transfer sewage away from the River Thames. Starting in Acton, West London, our tunnel will travel through the heart of London at depths of between 30 and 60 metres over 24 site locations, using gravity to transfer waste eastwards. Looking at the schematic shown on the screen and starting from the right-hand side, you'll see that the basic principle behind Tideway, which is intercepting a combined sewer overflow point, which then flows through an interception chamber, down the shaft, through the connection tunnel, and finally into the main Tideway tunnel. It's difficult to mention the project without mentioning the More by River strategy, which is developed to reduce the number of HEVs needed to deliver the project. Now, this has delivered numerous benefits by incredibly reducing our impact on the road network, on our vulnerable road users, and London's air quality. Compared to original estimates of HEV movements needed by the project, we've been able to reduce that number by an estimated 72%, and by using the river to transport materials, we've been able to avoid an average of almost 200 lorry movements a day. Passing on to Florin.
Hi, everyone. My name is Florin. Thank you all for joining us today. I've been lucky enough to be part of the team delivering the works at Victoria Embankment. And through the following slides, I will present the enabling works required for the shaft's excavation. So starting with the cofferdam construction, this is the first element of enabling works, started in September 2017 and finished in October 2018. Works have been carried out by the Flow JV Marine team. Victorian Embankment Windmill Cofferdam gained approximately 3,300 square meters within the foreshore of the River Thames. In short, the delivery team has used two 160-ton cranes, spud leg barges, flat-top barges, and pile hammers. AZ last and sheet piles have been drove into the ground for approximately 10 meters using the two cranes. Of them was being split in independent cells, and the two long sides have been tied together with rods and welded beams. See the picture on the right-hand side there. In between the sheet piles, 6A material was used to backfill. This material was only hydraulically compacted and did not require mechanical compaction. Before the cofferdam was closed, the GV has rescued from the cofferdam enclosure approximately 3,500 fishes. With the cofferdam closed, the Flow GV proceeded with the excavation of the hinterland silt and riverbed deposits in order to make way for the future working platform. The biggest constraint for the team has been management of third parties, and in particular consents approval to facilitate the works. The cofferdam, once completed, has become part of the EA flood defense until the new river wall is built. Next slide. The second element required for the shaft excavation to start was the second pile wall. These works started while the cofferdam was being built in the river. The retaining wall's scope was to mitigate settlement around third-party assets such as TfL disting line and Cadent and Thames water pipes network. The wall and its capping beam will also facilitate the construction of the CSO chamber roof slab. Barhale team, along with expanded piling, installed 81 numbered piles, 750 mm diameter, with a depth of 14 to 15.5 meters. And to carry out these works, a BG30 piling rig with a 60-ton crawler crane and a 13-ton excavator has been used. The biggest challenge for the team was the footprint available to deliver the works, the management of muck and storage and removal, concrete deliveries, reinforcement deliveries and storage, and piling rig exclusion zone to safely operate. All of these required a precise and a close management on a day-to-day basis. With all these constraints, the site team achieved an average progress of 2 to 3 piles every day. Next slide. The third element required before the shaft works commenced was the gas diversion. Victoria Embankment Service Subway is running between the cofferdam tie-ins and is located behind the existing river wall. The subway houses 2 cast iron pipes, and the designer assessment on these pipes has shown the possibility for these to fail during the shaft excavation works. What we see on the slides here is the north end pit. In the south, we've implemented a mirror pit, and in between, we had 110 meters of pipes to be installed. The diversion was implemented in 2 stages. Stage 1, where Barhale had to create the 2 openings in the existing service subway and another chamber adjacent to allow the installation of elbows on the pipeline. In stage 2 was Cadent had to install 110 meters of pipe and connect everything to the existing network. The site team had 2 major challenges to overcome. First was the network connection window, which starts in April and finishes in October. This is the only period when the supply can be diverted without affecting users, and missing this window would have meant the delay of the shaft works by 6 months. Secondly, was the implementation of temporary works to allow us to work around the live gas pipes and propping of the existing river wall when excavating behind it. Next slide. In October 2018, as we were finishing off the gas diversion works, Barhale team received access to the cofferdam and commenced the works for the 4th element required to start the shaft, the depressurization of the intermediate and lower aquifer in the area. WJ was employed to drill and install a set number of wells and undertake a pump test. With the information gathered from the pump test, the designer confirmed the designer had sufficient information to describe a robust dewatering system, which had a mixture of Lambert, Tannet, and Chalk wells, and was able to pump 150 liters per second if required. Due to a technique used to drill the wells, washing of fines usually occurs in granular material used in the twin wall cofferdam. This was a high risk for us, and to prevent occurrence during the construction of the cofferdam, steel tubes have been left in place at different locations. The wells have been drilled using a small rig and case rods with lost end bits. Once at formation, a plastic sleeve with perforation is inserted in the targeted area, and then operatives proceed with backfilling with shingle around the filter part, grout the remaining area, and remove the rods. Due to similar systems being implemented within Tideway Blackfriars and Albert sites, the lower aquifer target has been reached without any pumping from Victorian Embankment. Our last task before shaft excavation commenced was to install the bearing and contic piles. This facilitated the construction of the new river wall works and the CSO structures. The works have been carried out by expanded piling and have overlapped with the beginning of the dewatering works and these are presented on the right-hand side picture. The subcontractor installed 70 number 1.2 meter piles for the new river wall and 47 number 600 mm piles for the CSO structures. These had a depth of between 14 and 18 meters. Works have been carried out between the beginning of November 2018 and mid-January 2019. River logistics became our biggest constraint for these works. Without obstructing the navigational channel on the river and having consent to moor only one barge to the cofferdam, this meant that while cages got delivered to site, no muck-away operations took place. Soon enough, when you pile 18 meters deep and 1.2 meters wide, muck builds up quickly and you run out of space. It was a fine line to ensure sufficient cages have been delivered to site and sufficient time was allowed for the muck-away to take place. Any delays to the barges due to weather events set a delay to the site works. What we see on the left-hand side is a snapshot of the excavation works carried out to expose these piles in July 2020 and commence the RC works for the CSO structure. All of the enabling works require the high accuracy in planning and coordination of activities on site due to its confined nature. And the site team has done an excellent job at ensuring the highest health and safety standards have been followed and works have been completed without any delays to the overall scheme. And now I'm going to pass over to Ella.
Just moving on to the shaft sinking techniques. So the diagram on the screen shows the geological profile of Victoria and the outline of the shaft and tunnel in black. The various strata shown were taken into account to enable the team to make an informed decision surrounding the shaft sinking techniques chosen. This resulted in the use of a combination of segmental and SCL lining. The choice of segmental lining for the first 34 meters meant we were able to take advantage of sinking the shaft within the London clay strata, which was more preferable for this construction technique. Segmental lining comprised of 13 rings sunk using caisson method and 21 rings using the underpinning method. However, we did switch to SCL for the remaining 13 meters for the more complex Lambeth group, which includes challenging layers such as calcrete, sand channel, and the upper and lower mottled beds. The sand channel contained pressurized water of 200 kPa. So to begin shaft excavation and installation of the first segmental rings, 4 steps needed to be taken. So if you look on the left-hand side, step 1. So step 1, a 22 diameter initial excavation area was created within the cofferdam. This area took into account the shaft annulus, collar, and temporary drainage. We poured an initial 50 mm layer of blinding using a skip to allow us to assemble our cutting edge on solid ground. And on the screen, you can see this area labelled in orange on the bottom left-hand corner. Step 2 involved the cutting edge ring installation, which comprised of a total of 16 number segments, as shown in the green label. And each segment contains 6 number stiffeners and connected together using M24 bolts, as you can see on the right-hand drawing section. Step 3 involved this installation of the choker ring. This ring is 50 mm thicker than a normal shaft ring, which creates a void as the shaft is sunk, which you can see in the magnified red dashed square on the right-hand side of the slide. This void behind the shaft segments will be used for lubrication while jacking down the shaft, preventing the ground around the shaft from collapsing and also for grouting purposes. The last step before we could begin shaft sinking was to install the shaft collar, which involved installation of 15 number sacrificial legs shown in white dashed line for the jack and gallows base. Once installed, we were able to start reinforcement installation, including a safe batter on the edges of the excavation to a gradient of 1 in 5, and barriers installed 2 meters back from the edge. We also used core grid panels to separate the collar from the batter, and the shaft collar was approximately 1.2 meters deep and by 2 meters wide. At this stage, as you can see, the shaft collar is poured and the jack and gallows marked in white dashed line are installed. Now, the purpose of these is to put pressure on top of the segments and push them down. Each gallows is able to exert a pressure of up to 40 tons. The location and spacing of these is to exercise the pressure equally on the segments to avoid verticality and structural issues. However, when installing segments, we lifted and turned the rams. Now, you'll remember that I mentioned the 50 mm void behind the segments, created as a result of the choker ring being 50 mm thicker than the ordinary segments. This was used to pump the lubricant, which was made up of coarse lube, TK50 and TK60. This lubricant acts as support fluid to surrounding ground to prevent it collapsing and prevents friction. In general, once we began sinking the shaft using this method, we would push until the top of the segmental ring was 150 mm above the collar, and then we begin building the next one. The excavation process was carried out using 13-ton excavator, and forced air ventilation began when the depth of the excavation exceeded 10 meters, while gas detectors were used to monitor gas level for the duration of the shift. Once we finished installing our 13th ring using the caisson method, the next step was to grout all the rings and remove the cutting edge. The grouting process involves attaching grout guns into the segment hose to pump grout consistently and evenly fill the gaps. We started from the bottom and worked our way to the top, and this replaced the lubricant, which is displaced at the top. The presence of grout was checked using thermal camera, and once the grout was cured and we were satisfied with that, the cutting edge key was unbolted and burnt out, followed by the remaining of the cutting edge ring. We average about 2.17 rings a week, 420 tons of muck removed per week, and we had one instance of the self-weight of the segments resulting in the shaft sinking 100 millimeters over 2 days. Finally, we switched to underpinning when we had 21 rings remaining, and it took us about 8 days to mobilize.
Now, moving on to the underpinning section. This is a well-known technique in the industry that we all use in good ground. And to safely excavate and advance and install a ring, site team has used the following sequence. We dug the center of the shaft using an excavator and leaving a 1.5 burn, as we can see on the right-hand side picture. Carry out a shear vein test to confirm the ground conditions. Progress with the berm removal in quadrants. Break ground to the underside of the previous row of segments and excavate in depth to allow the building frame and segment plates to be placed under the previous segment, as we can see on the left-hand side bottom picture. Check the excavation profile against the segment thickness, then install 4 to 5 plates using this building frame. What is the building frame? Well, this is a frame made bespoke for this type of operations and can be used for different shaft segments by adding additional counterweights. Next slide. You can see in the top left corner the first key segment being installed. These segments are special and have one of the vertical edges inclined. This inclined edge facilitates the installation of the last piece, and with the segments being installed, the miners proceed with the circularity and lipping checks. What do I mean by this? Well, this means they will check the build ring diameter using a tape measure between the grout hole of the ring at the edge and at the edge between 2 segments on the opposite side. And then the lipping between the previous row of segments installed. Once the check confirms the requirements are met, the miners proceed with one of the most important operations, which is the backfilling to the underside of the segments and creating a seal using clay. The backfill and the seal is created for the back grouting operation. If this is not done properly, the grout will be lost and segments will have a void to the clay. This void can create settlement around the structure and damage third-party assets at the top. The grout used at Victoria was a wet mix designed with Hansen to suit the site requirements and comply with the specifications. Grout was pumped down the shaft using a pump and taps, as you can see in the middle picture. This tap had a pressure gauge installed and pressure was monitored so we do not exceed the maximum allowance specified by the precast manufacturer. A complete cycle was carried out in approximately 2 days. This technique allows much more control for verticality and circularity when sinking a shaft. Next slide. The picture from this slide, you can see the probing works carried out in the shaft during the underpinning section. The first level of probing was specified by the Permaworks designer at 12 meters above the SCL section and provided ground conditions reassurance. To probe, we use a hollow stem auger drilling technique, relative rapid technique, and samples retrieved provide reliable information on the ground conditions. This allowed the site team to schedule and confirm toolbox items for the SCL section. What is a toolbox item? Well, in short, the toolbox item are prescribed methods that are readily available for the contractor to use in order to facilitate the perimeter works, or methods that will deal with identified risks. These are the contractor planned control measures to ensure the works do not stop and carry in a safe manner. Next slide.
So moving on to the SCL. In order to supply concrete for the SCL works, we use a pre-blended dry mix and store this on site in 40-ton dry mix vertical concrete silos. The concrete is mixed on site by adding water at a controlled rate to the dry mix and discharged directly into the North Streamer concrete pump. Interface with other works in Cofferdam 1 and designated areas for certain activities were discussed and agreed during daily morning coordination briefings, as well as being clearly marked out on site. Two number cranes were used for the works. One 80-ton crawler within the hinterland of the cofferdam servicing the shaft, and another 160-ton crawler on top of the cofferdam as a backup. Cranes were used to install ventilation, viewing point, concrete static pump on surface, and a fixed supply to the transformer and lift the Normet Minimax spraying robots to the bottom of the shaft, as you can see labelled up on the diagram. To complete the shaft excavation, we should switch to SCL for the remaining 13 advances. Each advance is 1 metre in length. SCL comprised of 2 stages. The first stage is an initial sealing layer of 75 mil, which is sprayed onto the newly excavated ground to provide early support for the personnel working at the shaft or tunnel face. The second stage is the primary lining layer. This is 600 mil in total for the shaft and is sprayed in layers of 200 mil max. And this is sprayed once the full excavation round is completed. After installation of the last segmental ring, we proceeded to excavate the first SCL advance and apply a sealing layer. Following this, we needed to complete the dowel connection between the final segmental ring and the first SCL ring. As such, we installed the second part of the 25 diameter dowels into the segments to allow a minimum embedment into the SCL of 400 millimeters, as indicated on the slide by the blue coloured arrow. We then continued the SCL as per the RES. The RES is a required excavation support sheet, which details the sequence, tolerances, and other important information that must be followed. No SCL works can commence on site without an in-date published RES sheet. Each sheet is issued per advance, and as mentioned, the excavation SCL works related to that advance are detailed, confirmed, and communicated throughout the RES meeting. Attendees include the senior SCL engineer and representative from the main works contractors and the client. So in our case, the senior SCL engineer was the designer's representative from ACOM, and then we had representatives from Florin, Langrock, Barhale, Tideway, as represented by Jacobs. So following the first ring, our excavation sequence largely remained the same. So looking at the top left-hand corner diagram, we use the 13-ton excavator in pit bottom to bulk excavate stage A to create a perimeter berm. The berm is excavated in quadrants or halves, so in the diagram shown on the screen, we would have excavated stage B, prepared the vertical joint, and then applied a 75 mil sealing layer before moving on to stage C. All the details and sequences were detailed in the RES. It's worth noting we installed service support brackets at 4 metre centres on the wall of the shaft as we moved down, and this housed 4-inch steel concrete delivery pipelines, 4-inch steel compressed air pipelines, accelerator line, and other basics such as comm systems, gas detectors, and more.
Thank you, Ella. At the beginning of the SCL section, in order to further validate the ground condition, a second set of probes was prescribed by the Permanent Works designer. These are marked in the drawing with red. The activity was carried out 30 meters below ground level, and based on the discussion with the specialist dewatering contractor, further probing was carried out every second advance. Using this information, we validated the toolbox item prepared for the excavation during the SCL shaft works. Next slide. The only toolbox item required for the SL section was the dewatering of the 3-meter sand layer. The dewatering contractor prescribed the installation of one radial system of wells that provided local dewatering. A hollow stem auger technique was used to drill the wells, and where the ground was not suitable, we drilled using casing. Once the well was formed, a 40 mm perforated pipe has been installed and connected to a vacuum pump system. The well's array had a spread of 2 meters center to center. During these works, the site team has used this opportunity to install further wells for the tunnel first 5 advances. The dewatering system has proven highly effective and allowed the team to safely proceed with the next shaft advances. Next slide. Moving on to fatigue. For a while now, health and safety professionals within the construction industry have recognized the importance of tackling health issues and not just concentrating on safety. With fatigue, there is no silver bullet. You need a methodical approach, and this should start with a baseline assessment to understand the extent, impact, and causes of tiredness and fatigue. From there, you can amend policies, train key managers, and look at other possible interventions. As a result, from fatigue, we commonly see issues including poor health, increased level of stress and declining mental health, impaired decision-making, accidents and near misses while it's commuting, reduced coordination and poor communication. At Victoria, the site team received training from Barhale and Flow JV recognized mental health programs, and with the assistance from our health and safety advisors, we set up a working pattern that prevented increased level of stress, fatigue, and sufficient resting time. Constant health surveillance was also provided to blue and white collar personnel during these intense works. Next slide.
So to conclude the shaft SCL section, we completed the SCL drive in approximately 9 weeks, with cycle times averaging 24 hours, which included 10 hours excavating and 12 hours spraying. Other important points worth noting include staggering of radial joints to avoid alignment with previous joints, strict adherence to exclusion zones, including a minimum of 0.5 MPa compressive strength combined with a minimum of 45 minutes having been elapsed, ventilation using an extraction system, and finally careful consideration and planning into mitigating the risk of being unable to provide ground support should unforeseen circumstances occur. Measures to mitigate this at Victoria included sufficient SCL supply before commencement of excavation of unsupported ground, 2 compressors including a backup, 2 concrete lines including a backup, mains power supply and backup diesel generator, hand spraying with all the associated gear on standby in the event of robot failure, 24-hour technical support for the robot and pump provided by the manufacturer, second standby robot, backup concrete line, and finally, guaranteed replacement of a broken down robot within 24 hours. All of the above mentioned led to SCL wastage of only 68% within the shaft. Moving on to the base slab. So starting on 7 AM on a Wednesday and finishing up around 1 AM on Thursday morning, the base slab pour was successful. At 3 meters deep and 17 meters in diameter, it involved pouring an initial 100 ml blinding layer following completion of SCL, followed by steel fixing. A detailed thermal plan and pour plan alongside other key documentation meant key issues could be foreseen and mitigated. The use of thermal monitoring using thermocouplers meant we could monitor the maximum differential temperature to avoid thermal cracking. The pour took less than 24 hours and involved 70 wagons to pour the 510 meter cubed concrete pour. And moving on to the short connection tunnel. So the short connection tunnel links the Victoria CSO shaft with the main Tideway Tunnel. This is approximately 17 meters long, 3.6 meters in internal diameter, with an enlargement which increases diameter to 4.6 meters in the last 4 meters, as shown on the section on the bottom of the diagram. The lining thickness for the first 13 meters was 250 mil, and the enlargement section had a thickness of 300 mil. Now, the contractor was expected to encounter sand above the crown and in the upper quarter of the crown, while clay remained for the 2/3 of the rest of the base. Due to the stresses caused in the overall shaft lining by creating the tunnel eye, the design required reinforcing this area. We refer to this area as the connection tunnel portal. It required 3 layers of 200 ml SCL and rebar, which meant that the lining within the portal area combined with the original SCL was 1.2 meters, double that of the remaining of the liner. Once completed, the tunnel eye could be formed by stitch drilling and using an excavator. So excavation sequence. So based on the observations during shaft sinking, encountered ground conditions were expected to be sand and clay. And in the event that encountered conditions were different than those issued within the res, we needed to seek advice from the senior SCL engineer on site. For the first few advances, the general sequence we followed was pocket excavation. First, excavate a pocket at the top centre of the face, labelled 1 in the diagram on the top left-hand corner, and assess ground stability. Then a hole point followed. If conditions were stable, then we would continue excavating the pocket labelled 2. If ground conditions were not stable, then we would apply 75 mm SCL layer on pocket 1 before continuing to pocket 2. This process was applied to the pocket labelled 3 and then below access labelled 4. Once fully excavated and sealed, the full 250 mm SCL thickness round was applied to the crown, shoulders and invert. However, from advance 5, things did change. So overall, combination of measures were moderately effective, but were not sufficient to entirely eliminate instability. Pocket excavations had limited benefit, which meant that pockets that appeared to be stable following excavation became unstable over time due to groundwater movement or upon application of SCL. Securing the excavation above access as soon as possible became our top priority. Once secure, remaining excavation was generally incident-free. As a result, a sloping face of 1 and 4 was implemented from advance 5. The sloping face significantly reduced the incidence of ground being lost ahead of the face, but had no effect on ground stability. Heading a bench sequence was utilised upon approach to the TBM tunnel to minimise TBM tunnel movements. And this was effective at reducing lateral movements of TBM tunnel to about 10 millimetres maximum. So I'm just going to press play on this video. So from advance 7 to 13, we had significant water ingress, causing instability and localised washout of sand. As you can see in the videos shown, ground conditions degraded with the sand being so fine that it created issues with the SCL adhering to the face and round. Depressurization and ground treatment had been applied to control this, but with medium rate of success. Therefore, additional toolbox items needed to be implemented, which Florin will cover in the next few slides.
Thank you, Ella. So then in the next slides, we will present to you in short the prescribed toolbox items the site team prepared for the tunnel excavation, which are pipe arch, spiles, banker bars, and dewatering. For the tunnel excavation, the site team engaged OTB and WJ to prepare this set of toolbox that can be easily implemented when required. Next slide. To stabilize the ground in the tunnel crown, the temporary works designer prescribed the use of a pipe arch system for the first 11 advances and progressed with spiles for the remaining 7. The pipe arch system is a pre-support system used in weak ground conditions. The vertical alignment of canopy tubes is designed to be parallel to the tunnel alignment to minimize overbreak in the event of excavation breaking back to the canopy tubes. Spiles, again, are a pre-support system that is designed to be installed before the advance commences, and these are drilled in the tunnel crown in the direction of the excavation. This works, we had to use a specialized drilling rig. These machines are specially designed for tunneling works and can be used for canopies, spiles, banker bars, and probing. The pipe canopy had an overall moderate efficiency at minimizing ground loss for the tunnel crown, negligible improvement in face stability. The efficiency was reduced by inaccuracy of installation, tube alignment deviating over the length by as much as 300 mm, and resulting in increased spacing between the tubes beyond the capacity of sand to arch and self-support. Spiles had an overall efficiency negligible in minimizing ground loss from the tunnel crown and negligible improvement in face stability. Reducing spacing from 300 mm centers to 150 mm centers did not improve effectiveness. As a result of spiles inefficiency, the site team used banker bars for the remaining 6 advances. Next time. Banker bars. This is a temporary support of ground, mostly used in UK for vertical shafts. Horizontal use of this technique is not very common, but it's an extremely effective method at securing the excavation crown. To install the sheet piles, the team pre-drilled the tunnel face using the jumbo drill and created slots that acted like a guide wall. Then, using a 5-ton excavator equipped with a hammer, progressed driving the sheets following the tunnel alignment. We have achieved to drive each row of sheet piles approximately 2.5 to 3 meters. And this embedment allowed the site team to carry on a meter advance before stopping and installing another set of sheets. With this technique, we had minor issues with shotcrete bonding to the exposed surface of banker bars, and potentially this can be mitigated by pre-installing welded mesh to the sheet piles. It's a very effective method at securing the tunnel crown and keeping a stable excavation phase. Next slide. In conjunction with the pipe canopy, spars and anchor bars, the contractor installed wells from within the tunnel to dewater the sand layer. The specialist contractor used the Soilmec SM5 rig. This machine allows the arm to pivot on multiple axes, making it very effective for works carried out in confined spaces. You can see on the right-hand side picture the machine. Each well was connected to a new vacuum pump system set up inside the shaft. And this vacuum system improved the draw from the well significantly and was very effective at dewatering a high proportion of the sand mass, typically with a range between 3 to 4 meters. When the system was highly effective, the encountered sand had the tendency to dry out and induce cohesion. Due to irregular formation level of the sand channel, water moved freely below the installed level of points. Victoria Short Connection Tunnel ground conditions have proved to be one of the most complex and challenging environment from Tideway Central section, and all the toolbox items used required advanced planning and preparation. The implementation of these works was done within the confined spaces and proven to be complex, required experienced personnel to implement them. Next slide. Now, what we can see here are a few bullet points that the site team has put together to provide an insight to the challenges we have encountered within the last 3 years. First, the approval of precast rings was a lengthy process that required the support from all sides to get the product approved. For most other clients, the precast rings act as a temporary lining, which brings less scrutiny in getting the product to site. Segments, production surveillance, was as they've been part of the permanent works, now required the production surveillance and came under its own logistic challenges. Then the presence of others on site did not make the works easier and simpler. We constantly had to move the site layout arrangements to facilitate the different contractors on site. The supply of specialist equipment, such as building frames or jumbo drills, is strictly limited to some suppliers that might not have them in stock for hiring. This can cause unnecessary delays if not looked at it in detail before the works commence. The river logistics and the barge movements, being supplied by river and having to plan all the deliveries based on the tides was a challenge. This also meant that someone else was loading our barges with materials and equipment. The location of the consolidation center also came with its own problems, where this location was in a part of London that had a high probability of strong winds and in an exposed ground. The ground conditions for tunnel works, the challenging ground conditions made the tunnel excavation difficult and time-consuming. COVID-19 during the tunnel works, we've unfortunately had to be stopped, and we had to implement additional control measures to ensure the site is safe for personnel to carry out their works. Extra resources had to be brought in to ensure the works can be carried out without any obstruction in case one of the teams had to isolate. Then consents, the project is being delivered under the development consent order granted by the Secretary of State in accordance with Section 37 of the Planning Act. And due to this, to the disruptive nature of these works, the location and interface with multiple third-party assets, this proved to be a slow process and required a lot of close management to ensure the works can be progressed as planned. For example, to progress with the dewatering works and lower the level of different aquifers, the contractor had to provide to the parties involved hydraulic models, monitoring of impacted wells, pump test, and only then obstruction consent has been granted. These steps look simple, but they require time and resources from the project team.
So as well as the above mentioned by Florin, as Jacobs were appointed as principal designer on Tideway and from a CDM perspective, we needed to ensure that there was careful coordination, communication and elimination of any foreseeable health and safety risks to anyone affected by the work carried out, and where we could reduce or control those risks. So as an example of the number of parties involved, just for the connection tunnel, AECOM were the permanent works designer, COVI the temporary works designer, OTB the Cat 3 checker, and Flow JV the lead designer. So which highlights the importance of coordination and communication on a project of this scale.
The tunnel excavation and SEL demobilization was the last piece to be finished and allowed the above ground works to start. Since June 2020, site has constantly changed and day by day it looks different. The team at Victoria has done an excellent job to deliver complex and concurrent works, and I would like to enumerate just a few of them. The shaft and tunnel secondary lining, existing river wall demolition to allow the CSO chamber construction, completing 80% of the new river wall. You can see on the left-hand side picture, this encloses the shaft, and 70% of the CSO structure RC works. The latest achievement for the site was to install the last vortex pipe and inlet. This means we have completed approximately 80% of the RC works within the shaft footprint. The works at Victoria are planned to be finalized the RC works at Victoria are planned to finalize at the end of this year, and thereon Flow GV will continue for another year and a half with the architecture and landscaping works. I want to thank you all for listening to us today, and I hope you enjoyed the presentation. And hopefully soon we have other projects where we can present and showcase our work. Vic?
Thanks a lot for that, Florin and Ale. And it's really surprising to see the magnitude of the work involved, which is, you know, and especially given that the fact that the site's there in public eye, I often wonder how many people actually realise the magnitude of work that goes around to deliver such projects literally at their doorsteps. So I think on that note, I think we can move over to the Q&A now. So I'd like to request the attendees to ask any questions they might have using the chat feature on YouTube. And in the meantime, I've got one myself. So looking at the amount of dewatering that was done, I was just wondering what were the sort of settlement values that you got around the sort of local area from those dewatering works. Was the settlement impact substantial, or was it negligible?
The settlement from dewatering wasn't the one that was driving concerns. It was more the settlement that appeared from the caisson and underpin section. At that time, I know we've almost reached the maximum allowance, but after that, once we start applying the SEL layer, it sort of stabilized and got to a point where it was still and nothing moved after that.
Okay, that's good to know. And whilst we're waiting for questions from the viewers, I might as well ask another one. So I think Ale, you mentioned 68% wastage figure for the SEL used, and of course, you know, with the stress on achieving net zero in UK, is there something you thought we could do differently that would further reduce that wastage?
I think it comes down to planning efficiently and properly before we start. So a lot of the things that we, how we were able to reduce that number to 68 was a lot of planning in the beginning. So I think that's probably the most important thing. I don't think there's anything that we did there that we would take on to another project that we did differently. But I think, yeah, it definitely comes down to planning and, you know, for example, ensuring that we're not stopping for long periods of time because of the way we've planned the works. So, you know, we're not having to seal more than 75 mil at a time when it's unnecessary and that we could have avoided it basically, because all of that comes down to the wastage. So I think, yeah, it's just planning correctly.
Sure.
Usually you plan for about 100% wastage on shaft linings.
Yeah.
This all comes down to planning. Well spoken. We've got a few questions from on YouTube now. So I think Sarthak is asking, what was the angle of inclination of the pipe roofing? So I think that's the
pipe
pipe canopy.
canopy. The pipe canopy had an inclination. Well, it had a 100 mil at the end of the arch. This was to allow for them to, in case they deviate down, and they will protrude in the permanent works lining. So we set them up. I can't remember if it was 5% or 4%, but with the length of 11 meters, they will give you about 100 mil at the end. So yeah, that's
Sure.
how we.
There's another one on YouTube, which is the last ring of the segments fixed in place prior to starting the SCL works? Does it not continue sinking under self-weight?
At that point, we would have grouted behind the rings and waited for it to cure before we continue on with the SCL. So not really, no. Unless, Florin, you want to add anything?
No, once you're in underpinning, the shafts tend to stop sinking. In case, and yes, when you have the cutting edge and you have that transition, confirmed, you do lose a bit of height in the shaft, so you always stop slightly higher to allow for that.
Mm-hmm.
And then we've got one from Richard Lewis, and Richard asks, why was the underpinning technique not continued to the bottom? Why change to SCL?
As far as I remember from the discussions we had with the Permaworks designer, the hook stress that will be applied to these segments was higher than they will take. Plus, then you would have went from that cutting level to the sand layer. You had about 3 to 4 meters, which in sand, this is not a method that you will use.
Thanks for answering that. I think those were the only questions from YouTube. So if you are following on YouTube and if you've got any more questions, please feel free to raise them. In the meantime, another query from myself there. The enlargement section of the connection tunnel, I think I missed out on. Did you mention why there was an larger section closer to the main tunnel? Was it a hydraulic reason, or was it just based on the parent-child connection?
As far as I know from ACOM, the enlargement is due to fact at the end you will go in and start breaking those segments. So you want to have a large area that sort of traps and holds those segments together. Having a smaller area creates more risks. It means you have additional temporary works that you have to implement in the tunnel where it's easy to work. And yeah.
So the final lining still is of the same cross-sectional area, but it's just the final section of the temporary works was larger, or the SCL tunnel was larger. Thanks for that. Another reminder to those following online, if you've got any questions, ask them now. They've got a long list of questions I can quiz you on, so I might as well ask another one. So, I mean, it's fantastic to see, the amount of work you have been doing at Victorian Embankment Foreshore. Of course, you are, an integral part of the BTSYM community. In terms of key lessons that you learned during your time spent on the project and whilst overcoming the challenges that the project kept on throwing at you, what is the key takeaway that you'd like to share with the rest of the YM community? And it can be in terms of technical, but even in terms of, if you've learned new managerial skills. Um, is there something specific you'd want to highlight to them?
I would say, just from my perspective, maybe Florin has a different one, is collaboration. I think at Victoria, there's a lot of different parties involved, like I mentioned earlier. And I think when it comes down to it, so we had Jacobs representing the Thames Tideway, Barhale and Flow JB. I think a lot of it came down to collaborating with one another and communication. Because a lot of the time, people want to, we want to just get on with things and to get them done. But we had a really, really good team at Victoria, and there was a lot of communication, collaboration, various team meetings, etc., which made, I think, what we've done as successful as it has been. And I think, moreover, that really carried through when COVID hit and we stopped tunneling. And then we had to come back in afterwards, in the beginning of COVID to, finish off the tunnel, and how well communication, collaboration worked there to allow us, to resume activities and, get it done. So I think it sounds quite basic to say collaboration, communication, but for me, it kind of highlighted just how important it is. This is probably a key takeaway for me. Maybe Florin has another one.
For me, probably was consent approval and managing third parties. It was a lengthy process to get the plan works approved. You had so many parties that had to accept how the design was submitted, and then how you're going to implement it on site. And this brings a lot of time before you actually undertake the works. So yeah, you need to plan that activity correctly. But as Ella said, all the collaboration and all the discussions, the open discussions we had on site, we managed to overcome them, and yeah, it's fine.
No, I think those are very, very valuable comments from both your sides. And I mean, talking about third parties, Florin, I've been involved with sort of asset protection on the eastern section of Tideway, and the lesson I've learned is collaboration is the key. Early doors stakeholder engagement is you can't really beat collaboration. It makes life for everyone easy and makes sort of ensures your delivery strategy is robust. Fantastic. I think we haven't got any more questions on YouTube, so I might wrap up with asking a final question, which was COVID. So, just out of curiosity, what controls you had on site to mitigate the risks due to COVID? You had or you currently have?
Well, as you're aware, at I think on the 23rd or 24th of March, Tideway sites have all closed down, and everybody had about 5 to 6 weeks to progress with a plan and how to safely reopen the sites and what control measures we need to implement depending on the situations we were all in. And for us at Victoria, was a good period where we managed to plan and everything. One-way system routes, stagger shift start times and ends, breaks as well. Coordinated the welfare management in terms of cleaning it and ensuring that there's sufficient canteen space for people to rest. Same for the site, implemented the masks and implemented zone areas as proximity. If you work in proximity to somebody else, you had less than 2 meters, then face masks were mandatory. Improved ventilation inside the tunnel as well. Fresh air we've introduced another ventilation in there just to ensure that fresh air is pumped in. Yeah, I mean, it was a challenging period, but we went okay through it. The third team obviously helped and gave us a boost in terms of security. We were doing the tunnel at that time and only had two teams, and the third team coming to sites gave us that security that in case some of the team members do fall sick with this virus, then we could replace and we can swap people around and get the job finished in there.
Well, it has indeed been a challenging year, but it's good to see you had robust controls in place. I think on that note, we can call it a wrap for the day. So I'd like to once again thank both of you, Florin and Ale, for sharing the experience you've gained on the project with us today. And it was, I mean, very. Oh, we've got another question, but sorry, we might answer that question after the lectures. But yeah, it was very enlightening to see the challenges you faced and how you overcome it. So once again, thanks a lot. But before officially closing today's lecture, I've got a few announcements to share with the rest of the audience. So I'll take control of the screen now. So yeah, just a few announcements before we wrap up. And that's mostly to do with upcoming lectures and other things we've planned in the coming months. So the first one is just a reminder that the deadline for the bursary for the MSc in Tunneling and Underground Spaces at the University of Warwick has been extended to the 30th of June. So if you are interested in continuing your learning journey further, you can apply for the University of the MSc at University of Warwick, and also the bursary of up to £20,000 to support your time at the university. Next one up on the list is the BTS CPD course that is being offered these days. So it's a joint course between BTS and the University of Warwick. The next one is on tunnel design, which starts actually next week, but I think there might be a few more places available. So for further information, please go on to britishtunneling.com and you'll be able to find the booking link and the more information on the cost of the course. Next up, Thursday next week, there's a BTS evening lecture about Hinkley Point C. Again, streamed live on YouTube. So if you're free that Thursday, do dial in. Continuing the series of lecture, we've got the next BTS YM Lunch and Learn scheduled on the 19th of August, midday again, and that will be about Warsaw Metro Line 2 extension. That's delivered jointly with the Polish Tunneling Society young members. And then the final one in the lecture series, we've got a lecture by Mike King on design of gaskets for segmentally lined tunnel. That is not a lunch and learn, that will be an evening lecture on Thursday the 9th of September. Moving on, just a reminder, exhibition stands are open for general sale for the BTS conference scheduled for September this year. So if your company would like to exhibit your work at the store at the stands, do get in touch with the Tunneling Journal team. And then, of course, as most of you would be aware, we're celebrating the 50th anniversary of BTS this year, and as a part of that, the BTS has commissioned Nancy Kerr to compose a suite of songs dedicated to tunneling and tunnelers, and you can actually listen to them online by logging on to the link shown on your screen.